Welcome to The Explainer. Today, we're going to crack open the code that basically runs the modern world. It's the language behind almost every app, website, and service you use, every single day. We're talking about SQL.
So let's start with a simple question. Ever stop to think about how your favorite streaming service just knows exactly where you paused a show, or how an e-commerce site keeps your cart full for days? The secret behind all of that magic is a database. And the special language that lets us talk to it, that's SQL.
Now, the most common kind of database out there is a relational database. And really, the best way to picture it is as this perfectly organized digital library. Your data isn't just thrown in a big, messy pile. No, it's meticulously sorted into tables. Tables with neat rows and columns, just like books on clearly labeled shelves. Okay, so if we have this amazing library, how do we communicate with it? Well, we use a special universal language, SQL. It stands for Structured Query Language. And it's the standardized way we talk to these databases, to build their structure, to manage the information inside, and, most importantly, to ask for exactly what we need. You might be thinking this is some brand new, cutting-edge tech, right? Well, actually, SQL has been the trusted backbone of the data world for about half a century. So let's do a quick flyby of its journey, from a research project to a global standard. It all started back in the 1970s, inside an IBM research lab. It was originally called SQL, but the real turning point, the thing that made it a powerhouse, happened in the mid-80s. When it became an official standard, first by ANSI and then ISO, it was a huge deal. It was a promise to developers that the SQL they wrote would work pretty much anywhere. And that right there cemented its role as the world's universal language for data. All right, so how does this thing actually work? I know, a whole programming language can sound intimidating, but the good news is we can break down almost everything SQL does into three really simple ideas, using our library analogy as a guide.
Think of it like this. First, you have to actually build the library. You design the shelves, and you label all the sections. Second, you have to manage the books. Putting new books on the shelves, updating their info, or maybe taking some away. And third, the really fun part, you get to ask the librarian to find the exact piece of information you're looking for.
So that first step, building the structure, is handled by something called Data Definition Language, or DDL. These are the commands that are basically the blueprints for your database. Before you can store a single piece of information, you have to use DDL to define the tables and columns where it's all going to live. Let's look at a classic DDL command. Create table. It's super readable. We're literally telling the database, hey, create a table for me and call it employee. Then we tell it what columns we need, a name and an email, which are varchar. That's just a fancy word for text. And Adobe for a date. And boom. Just like that, we've built our first digital shelf. It's empty, but it's ready.
Okay, once our shelves are built, it's time to actually fill them up. And for that, we turn to Data Manipulation Language, or DML. These are the commands for doing the real work, adding, changing, and deleting the data itself. This is all about managing the books in our library.
The insert into command, it does exactly what it sounds like, right? With this one simple line, we're adding a new employee. We just tell the database to insert into our employee table. We specify which columns, name, and email, and then we provide the values we want to put in there. It's incredibly intuitive. And that brings us to the third and honestly the most powerful part of SQL. This is the part you'll use constantly. It's asking for information with Data Query Language, or DQL. This is the whole reason we bother organizing everything so perfectly, so that we can ask questions and get answers instantly. So to see this in action, let's use this simple employee table. We've got a few people here, each with an ID, name, department, and salary. Now, let's say your boss comes over and asks a very specific question. Hey, can you get me a list of everyone on the sales team and what we're paying them? So, how do we translate that question into SQL? We use the most famous command of all, select. In plain English, what this query is saying is, select the name and salary columns from the employee table, but only where the department column is equal to sales. And just like that, the database filters through everything and gives us back just John and Sam.
That's the power of a query.
Okay, so this language is from the 1970s. In the world of tech, that's practically ancient. So why on earth is it more important today than it's ever been? Let's dig into why SQL is still the absolute bedrock of the data world. SQL's staying power really comes down to this incredible mix of features. It is wicked fast at finding data. Its standards mean it's universal. It's got serious built-in security. It can scale from a tiny personal project all the way up to a massive global system. But maybe the coolest part is that it's a declarative language. You just tell it what you want. You don't have to tell it how to get it. The database figures out the best way to do that for you. That's a game changer.
On top of all that, SQL databases are built to be rock solid and reliable. They follow a strict set of rules called the ACID principles. Now, we don't need to get lost in the weeds here, but what it means for you and me is that for really critical stuff, think about a bank transfer or an e-commerce checkout, SQL guarantees that your data is always correct, always consistent, and never gets corrupted.
Of course, technology never sits still. A while back, a new kind of database started popping up to handle different kinds of data problems. And that leads us to one of the biggest conversations in data today: SQL versus its younger cousin, NoSQL. So what's the difference, really? Well, it mostly boils down to structure and scale. SQL databases love that rigid table-based structure we've been talking about, which is absolutely perfect for things that have to be consistent, like financial data. NoSQL databases are way more flexible, which is great for messy, semi-structured stuff like social media posts. And when it comes to getting bigger, SQL usually scales up by getting a more powerful server, while NoSQL scales out by adding more servers. At the end of the day, they're just different tools for different jobs. So if we're going to sum it all up, it really comes down to this. We can collect these enormous mountains of raw data, but honestly, that data is pretty useless on its own. SQL is the bridge. It's what connects that raw data to the meaningful, actionable insights that actually drive decisions in business, science, and tech. And I'll just leave you with this one last thought. We're always hearing that data is the new oil. Well, if that's true, just imagine what you could discover, what you could create, what you could build once you learn the language that actually drills for it. Thanks for joining the Explain. All right, so you've got the hang of Select, right? You can grab data. But what happens when you grab, well, way too much? That's what we're tackling today. This is the next big step in your SQL journey: filtering. We're going to learn how to slice through all that noise and find the exact piece of information you're looking for. Let's jump right in.
You know, no matter what you're working with, customer info, product lists, you name it, databases are just huge. We're talking thousands, sometimes millions or even billions of rows of data. And trying to look at all of that at once, it's just a lot. It can be totally overwhelming.
So when you're staring at this mountain of data, how in the world do you find that one thing? You know, that one specific customer you need to look up, or that single transaction that seems off. It feels impossible, right? It's the classic needle in a haystack problem. Okay, so let's frame this a different way. I want you to think of yourself as a data detective. Seriously, the database, that's your crime scene. It's just full of clues, right? And your job is to use the right tools to sift through it all, to find the real evidence and ignore everything else. And that brings us to your number one tool, the most essential piece of kit for any data detective, the where clause. This is it. This is your magnifying glass. It's what lets you tell the database, hey, don't show me everything, show me only the stuff that matches these specific conditions. And you know what's so great about it? The syntax, it's just so intuitive. It practically reads like a normal sentence. You're literally telling it, select these columns from this table where some condition is met. It's super simple, super direct, and honestly, it's a game changer. Okay, theory's great, but let's see this thing in action. Let's open up our first case file. We're going to be digging into this customers table. As you can see, it's got stuff like names, ages, salaries, and where they're from. Our mission? To interrogate this table and pull out some very specific people. All right, first question for our database. Let's keep it simple. We just want to find all the customers from the USA. So we write our query. We say select everything, which means select everything, from customers where country equals USA.
And here's a super important tip. Whenever you're working with text, what we call strings, you've got to wrap them in single quotes. Don't forget.
And boom, just like that. The database does all the heavy lifting, scans the whole table, and hands us back just 2 results, Ramesh and Mukesh. Everyone else, filtered out, gone. See how powerful that is? One little line of code and we slice right through the noise to get our answer. That's the where clause for it.
So that equals sign we just used, that's called a comparison operator. And it's just one of the basic tools or interrogation techniques you have in your detective bag.
So here's your main toolkit. You've got your basic equals. But you can also check if something is not equal using the exclamation point equals. And then, of course, you've got all your standard number comparisons. Greater than, less than, greater than or equal to, and so on. These little symbols are the building blocks for asking really, really specific questions.
But you know, a real detective almost never solves a case with just one clue, right? The magic happens when you start connecting the dots, when you link multiple pieces of evidence together. Well, guess what? We can do that in SQL too.
The way we do this is with something called logical operators. And the first one you've got to know is AND. AND is super straightforward. It just tells the database, hey, I need all of these conditions to be true. So it's like telling your partner, okay, the suspect has to be over 30 and they have to make less than 4,000. Both things have to check.
So this is what our query looks like now. We're selecting everything from customers, where the age is greater than 30 and the salary is less than 4,000. We're chaining our clues together.
And check out the result. We get just 3 people, Ramesh, Kamal, and Hardik. Now think about what just happened behind the scenes. The database looked at every single row. It found some people who were over 30, sure, but their salary was too high, so nope. It found other people with the right salary, but they were too young. Nope. Only these 3 individuals ticked both boxes. That's how AND helps you zero in with incredible precision.
Okay, so here's the bottom line. AND makes your search narrower, more specific. Both things must be true. Now, its counterpart is OR, and it does the opposite. It makes your search broader. With OR, only one of the conditions needs to be true. That's perfect for when your clue is like, the suspect was in this location or that location.
All right, but let's get real for a second. In an actual investigation or just in real-world data, you don't always have perfect information. What if your witness says, I don't remember the whole name, but I'm pretty sure it started with a K. Now what do? You don't have the full name to search for. All you've got is a partial clue.
Well, for exactly this kind of situation, our detective kit has a special tool. It's called the like operator. And it's built for pattern matching, basically for finding text when you only know part of it. It's perfect for finding something that's, well, like the clue you have.
Like has a secret weapon, wildcards. The most common one you'll use is the % sign. Think of it as a match anything character. It can stand for 0, 1, or a whole bunch of characters. Then there's the underscore, which is a bit more specific. It stands for exactly 1 character. Using these 2, you can create some really flexible search patterns.
So let's solve our starts with K mystery. The query looks like this. We select customers where the name is like K%. That little pattern, K%, is telling the database, find me any name that starts with a capital K, and I don't care what comes after it.
And there you have it, Kaushik and Kamal. The database found them instantly. So even with a fuzzy partial clue, like let us crack the case. This is one of those tools you'll use all the time, because real-world data is almost always a little bit messy.
Okay, let's boil this all down. What's the crucial takeaway here? You've just armed yourself with a whole new set of fundamental tools for your data detective work.
So, think about your new toolkit. Where is your all-purpose magnifying glass for filtering? Your comparison operators, the equals, the greater than, those are for asking direct, pointed questions. The logical operators, and or, are for combining your clues to build a solid case. And like, that's your secret weapon for chasing down leads when the trail goes cold.
So now you've got the tools. You have the power to dive into those huge data sets and pull out exactly what you need. So the only real question is, what are you going to find? What mysteries are you going to solve with this? Thanks for tuning in. All right, welcome back.
In our last explainer, we talked about a database being like a giant, super organized library. Well, today, we're going to learn how to actually walk in and ask that library for a specific book. We're covering the two most fundamental words in all of SQL, select and from. And by the end of this, trust me, you'll be writing your very first queries.
I mean, think about it. Databases today can hold millions, even billions of records. It's this vast, swirling sea of information. So the question is, how do we even begin to talk to it? How do we ask it to pull out that one single tiny drop of data that we actually care about? Well, that's the exact problem SQL was invented to solve.
So, let's meet our guinea pig for today. This is our customers table. It's pretty simple, right? It's got an ID, a name, age, salary, and where they live. Now here's our goal. We only want to see a list of customer names and their ages. That's it. For right now, we don't care about their salary or what city they're in. So, how do we ask the database for just those two columns?
To ask that question, we have to speak the database's language, and that language is SQL, Structured Query Language. It's basically the universal way we chat with almost every modern database out there.
To get even more specific, the part of SQL we're using today is called DQL, which stands for Data Query Language, and it does exactly what it sounds like. Its whole job is to query or ask for data that's already sitting in the database. It's the dialect we use when we have a question.
And within that dialect, there is one single command that is the absolute king. It's the cornerstone of pretty much everything you're going to do. It's the word you will type more than any other, and it's called select. This is where every single question starts.
Okay, so let's break this down. Our first command, select. This is always the first part of your query, and it's all about answering one simple question. What information do you want to see?
Think about it like you're back in that library. You don't just walk up to the librarian and say, "Give me information." No, you get specific. You say, "I want the book's title and the author's name." Well, select is you doing exactly that. You're telling the database, "Hey, out of all the columns you have, these are the only ones I want to see."
And this is where select gets really, really useful. On the left, you can see we can be totally laser-focused. We can say select name, age, and that's all we'll get. But what if you're just exploring? What if you just want to see everything? Well, that's where that little star symbol on the right comes in. Select star is the universal shortcut for give me every single column you've got. It's super handy. So we've told the database what we want. Great, but that's only half the puzzle, right? The database's next logical question is, okay, but where do you want me to look for it? And that is the job of our second command, from. Let's jump back to our library one last time. After you tell the librarian you want the title and author, you have to tell them the name of the book, right? The from clause is you doing just that. It's you telling the database the exact name of the table you wanted to pull that information from. You can't just select columns out of thin air. You have to say where they're coming from. And that's really it. That's the beautiful two-step logic of your very first SQL query. Step 1, select the columns you want. What do you want to see? Step 2, tell the database where they are from. Where is it? What and where? That's the whole game right there.
Okay, enough theory. Theory time is officially over. Let's put these two building blocks together and write our very first real, live, working query. Let's ask our database for the name, the age, and the country of all of our customers.
And here it is. Just look how clean that is. It's a perfect translation of our question. Select name, age, country. That's the what. From customers. That's the where. We are asking, crystal clear, for 3 specific columns from one specific table. That semicolon at the end, that's just us telling the database, okay, that's my full command. Go. And when we hit enter and run that simple 2-part command, the database gets to work and gives us this. And this perfectly shows the power we now have at our fingertips. And there you have it. Now, look closely at what we got back. More importantly, look at what we didn't get back. There's no ID column. There's no salary. There's no city. We got exactly what we asked for. Nothing more, nothing less. Just the name, age, and country for every customer. That is the incredible precision of writing a good query. So why is this such a big deal? I mean, who cares, right? Well, because select and from aren't just little commands you've learned. What you've just done is the absolute rock-solid foundation of all data analysis, all data science, pretty much everything. Before you can do any of the fancy stuff, you first have to get the data. And now you know how.
And hey, you don't have to take my word for it. IBM themselves put it perfectly. SQL has become the backbone of modern database systems. Think about it. Every single time you use an app on your phone, or check a website, or look at your bank account, it's almost guaranteed that queries just like the one you literally just wrote are firing off in the background, fetching your information.
So let's just recap what you've actually accomplished here. You can now officially read data from a database. You understand the two most important commands, select and from. You get that this is the starting line for all data analysis. And, most importantly, you have officially written your first real SQL query. Seriously, congratulations. That's a huge step.
But this brings up a new question, doesn't it? We're great at selecting columns now, but right now we're getting back all the rows. We're getting every single customer. What if we don't want every customer? What if we only want the ones from the USA? Or maybe just the ones who are over 30? How do you start to filter your results? Well, that is the perfect question, and it's exactly what we're going to cover in our next explainer. See you then.
Hey, welcome back to the explainer. So last time, we got pretty good at filtering data using the where clause, right? Well, today, we're taking the next big step. We're going to learn how to take complete control over the results your query spits out. Okay, so picture this. You've written what you think is the perfect query. You've got your select statement, your where clause is dialed in, you hit run, and what you get back is, well, it's just a mess, a total jumble of data. I mean, the right information is technically in there, but good luck finding it. Sound familiar? I bet it does. Yeah, take a look at this, for example. We're pulling vendor booth assignments, but because there's no logic to the order, it's just random. You see dates, vendor IDs, booth numbers, but if you're trying to track a specific vendor or see what happened on a certain day, it's a total headache. But what if we could just tell the database how to show us this stuff? You know, impose our own order on the results. Well, you absolutely can. And it all starts with one simple idea: sorting. So the first tool we're going to grab is the order by clause. And honestly, it does exactly what the name says. It lets you sort your results. You can sort by one column or even stack up multiple columns to get a perfectly organized list. And just look at the difference. One single line of code. That's it. We add order by, and the exact same query now gives us this beautiful, clean table. See how it's all sorted by date first, and then within each date it's sorted by the vendor ID? Instantly, this data goes from being a mess to being totally clear and usable. And you have total control over the direction too. By default, SQL sorts in ascending order. That's A to Z, or lowest to highest number. We call that ASC. But if you want to flip it and see the highest values first, you just tell it DESC for descending. It's that easy. But you know, sorting is really only half the story here. To really get control, we need to pair it with another powerhouse command. This quote right here from Renee Tiate's book, SQL for Data Scientists, is actually the key to the whole thing. It gives us a massive clue about a really important order of operations, and it introduces our second command for today: limit. Now, the limit clause is just beautifully simple. All it does is tell the database, hey, just give me this many rows. You write limit 5, you get 5 rows back. You write limit 100, you get 100. It's a super straightforward way to manage how much data you get. So why bother with limit? Well, for one, it's awesome for just getting a quick peek at a massive table without having to wait for the whole thing to load. But its real superpower is finding the top or bottom results. You know, like the top 10 sales or the bottom 5 performing products. And that little warning there, but only when used correctly, that's the key to everything we're talking about today. So that brings us to the big question, right? How do you make absolutely sure that the 5 rows you get back from your limit clause are the exact 5 rows you actually want to see? Okay, here's the secret. It's all about SQL's order of operations. This is so important. First, the database runs your order by. It sorts the entire set of data, all of it, behind the scenes. Then, and only after that huge sorting job is done, it looks at your limit and just chops off the number of rows you asked for, right from the top of that newly sorted list. All right, let's see this power combo in action. We'll set a simple goal. Let's go into our products table and find the 5 products with the absolute highest product IDs. And boom, here's the query. We select the product ID and name, like usual. Then, and this is step 1, we order by product ID DISC. That puts the highest IDs right at the top. Then, step 2, limit 5 comes along and just slices off those top 5 for us. That's it. That's how you get a top 5. You sort first, then you limit. This little trick has a name, by the way. We call it the top N pattern, and it is a fundamental skill for anyone working with data. Seriously, finding the top 10 salespeople, the 3 least popular web pages, the 5 most expensive items. It's all done with this exact same pattern. Order by, then limit. So, let's just quickly recap the big takeaways here. Order by is what you use to sort your data. Limit is what you use to restrict how much you see. And the real magic, the secret sauce, is that order by always runs before limit. When you put those two together, you can find the top N or bottom N of absolutely anything. So now you can organize your rows and you can limit them, which is awesome. It's a huge step forward. But what if you don't actually care about the individual rows anymore? What if you want to start summarizing them, counting them, finding the average price, or summing up total sales? How do we go from just listing data to actually summarizing it? Well, that's exactly what we're going to dive into next.
All right, welcome to the Explainer. Today, we're going to tackle something that is just absolutely essential for anyone working with data. We're talking about how you take a huge, messy table of raw information and turn it into a clean, powerful summary that actually tells you something. Okay, so picture this. You get a database, and it's got thousands, maybe millions of rows. Every single sale to every customer, every single day. I mean, there's a goldmine of information in there. But just looking at it, it's just a wall of noise. How do you possibly start to make sense of it all?
Yeah, take a look at this. This is a perfect example of what I'm talking about. You could see, okay, customer 4 bought something here, and then again over here on the same day. But if I were to ask you right now, who were our most valuable customers? Or what were our total sales last Tuesday? You'd be stuck scrolling forever, trying to add things up in your head. It's just not going to work.
All right, so here's the game plan for today. We'll start by digging into that challenge of raw data. Then we'll meet our toolkit, these things called aggregate functions. After that, we'll unlock the real magic with something called group by. And then we'll put it all together to answer some real questions and talk about why this skill is such a game changer.
Right, so let's start with the big problem here. The core issue is that looking at data one row at a time, while it's super detailed, it just doesn't answer those big picture questions. We need a way to boil it down, to summarize it, without losing all the good stuff.
It's really about changing your perspective, right? You need to stop looking at every single tree and finally see the whole forest. And lucky for us, SQL has the perfect tools to help us zoom out. And our first set of tools are called aggregate functions. All right, let's meet the team. There are 5 key players here, and these are special commands that do one calculation over a whole bunch of rows and give you back just a single summary answer.
First up, you've got count, and it does exactly what it sounds like it does. It just counts things. It's fantastic for answering any how many question, like how many sales did we have yesterday? But usually, how many is just the first question, right? The next one is how much?
And for that, you need sum. This is your workhorse for getting those big totals, like total revenue or total quantity sold. Now, if you know the total sum and you know the total count, what's the next logical step? Well, you want to know the average, don't you?
And that's where AVG comes in, which, you guessed it, calculates the average, or the mean. It's great for finding that typical value, like the average price of something. But you got to be careful with averages, because they can hide the really interesting stuff, the outliers, the extremes.
So to find those extremes, we've got min. This is how you find the absolute rock bottom value in a column. It's perfect for finding, say, the lowest price you've ever sold a product for.
And of course, on the flip side, you have max, which finds the highest value. This is how you spot your biggest sales or your most expensive products. So these 5 functions,
They're your starting toolkit. But honestly, on their own, they're kind of limited.
This is where things get really interesting. Because those functions are useful, sure, but the real magic, the thing that really levels up your data skills, happens when you combine them with the group by clause.
Let me show you exactly what I mean. If we just take an aggregate function, like sum, and run it on our whole purchase table, what do we get? We get one number, just one single number. Sure, it tells us the total number of items we've ever sold, but so what? It doesn't tell us much, does it?
And that's the key, right? This one big number, it's kind of useless for comparison. We don't want just one massive summary for the entire history of the company. We need summaries for specific groups of data. How do we do that?
And that is exactly what group by does. It's the instruction that tells the database, hey, hold on. Before you do that big sum or count, I want you to make some buckets first. Put all the rows that have the same value for, say, customer ID into their own bucket. Then do the math for each bucket separately.
And look at this. This is the transformation in action. It's beautiful. We've told SQL to count the purchases, but to group them by the date and the customer ID first. We didn't just get one big number, we got a whole table of summaries. We can see exactly how many purchases each customer made on each specific day. Now that is useful information. You can actually do something with this.
Okay, so we've got the basic tools down. Let's ramp it up a notch and tackle a question that's a lot more like what you'd get asked in the real world.
So, how much did each customer spend with each vendor? To figure this out, we can't just use one table. We're going to have to bring information together from a few different places: customer info, vendor info, and the purchases themselves. And then we can summarize it.
And boom. Look at this result. This is the payoff right here. So what do? First, we joined our tables together to connect customers to their purchases and vendors. Then we used sum to add up the money for each sale. And the final critical step, we told it to group by the customer and the vendor. And just like that, you get this perfectly clean report that answers the exact question we were asked. So you might be thinking, okay, that's a neat trick. But I gotta tell you, this isn't just a trick. This skill is absolutely 100% fundamental for anyone working with data.
Think about it. Pretty much everything you do in data analysis is built on this foundation. Creating those summary reports for your boss, that's just aggregation. Powering those cool interactive dashboards in a tool like Tableau, that's group by, working hard behind the scenes. Building clean data sets for deeper analysis, you're going to be aggregating. And for all you data scientists out there, this is feature engineering 101. These aggregated values are the very things you feed into your machine learning models.
So learning to summarize your data, it's not just about reporting on the past. Every time you create one of these summary tables, you're creating a new lens to look at your data. And once you can clearly see the patterns of what did happen, well, that's the first and most important step to making a really good prediction about what's going to happen.
Welcome to The Explainer. This is where we make code feel less like code and more like a story. And today, we're going to tackle one of the most important tools in any data toolkit, SQL joins, by telling a classic arranged marriage story. So, picture this. You've heard this story before, right? It's a tale of two families, a unique relationship they're trying to forge, and two separate lists that hold all the details of their eligible children.
All right, so let's set the scene. On one side, you have the Sharma family, and they've got their own little diary, a list of all the eligible bachelors in their family.
Now, in the world of data, we'd call their list a table. Let's call it the Latke_Wally table, or the groom side. It's simple. It has the name of each guy and, this is key, the city they live in. So we've got Rahul in Delhi, Amit in Mumbai, and Samir down in Pune.
And on the other side of the story, we've got the Varma family. No surprise here, they have their own list, their own table. We'll call this one the Ladkiwale table, or the bride side. And here we have Priya from Delhi, Sneha from Bangalore, and Ritu from Mumbai. Two separate families, two separate lists.
Okay, so here's the catch. Both families are interested in making a match, but they have one non-negotiable rule. The boy and girl have to live in the same city. So the big question is, how on earth do we compare these two separate lists to find the matches? And this, my friends, is where our hero of the story makes its grand entrance.
SQL joins. The groom's list is one table. The bride's list is another. And that process of connecting them, based on a shared value, in this case the city, that's exactly what a join is designed to do.
You know, in the real world, data's almost never in one giant perfect file. It's scattered. You've got customer info here, their order history over there. Joins are the fundamental tool we use to bring that scattered information together, to see the whole picture, to find the meaning. It's our digital matchmaker.
All right, so let's dive in and meet the 4 main types of joins. Each one tells a slightly different part of our matchmaking story. First up, we've got the inner join. I want you to think of this as the rishta pakka join. It means the deal is done, the engagement is finalized. It will only show you the pairs where the condition, living in the same city, is met in both tables. No exceptions.
And the code for this? It's so straightforward. We just say, hey, select the names and the city from the Ladkiwali table. Then, we interjoin it with the Ladkiwali table on the one condition that their city column is a match. That's it.
And boom, here's our result, the perfect matches. Rahu from Delhi gets paired with Priya from Delhi. Amit from Mumbai gets paired with Ritu from Mumbai. Notice who's missing? Samir and Sneha. Why? Because they didn't have a match in the same city. The inner join only cares about the successful connections.
Okay, next up, the left join. Now, let's imagine Mr. Sharma from the groom's side. It's a bit particular. He comes to the matchmaker and says, look, I want a list of all of my boys no matter what. If they have a match, great. Put her name next to his. If not, just leave it blank. But every single one of my boys better be on that final list.
And check out the code. It's almost identical. The only thing we change is the word inner to left. That one word tells the database, hey, the table on the left, the Ladkiwali table, is our priority. Show me everything from that one.
And here is the exact list Mr. Sharma asked for. See, all 3 of his boys are present and accounted for. Rahul and Amit have their matches, but poor Samir from Pune, since there was no one from the Verma family in his city, his match comes back as null or empty. That's the power of a left join.
So if you understood the left join, you're already one step ahead of me. The right join is, well, it's the exact opposite. Now it's Mrs. Varma's turn. She says, forget the boys. My daughters are the priority. I want a list of all my girls. If you found a match, fantastic. If not, I still want to see their name on my list.
And the code does exactly what you'd think. We just swap out the command for right join, which tells the database to prioritize the table on the right. In our case, the Ladkiwali table.
And this is the result. All 3 of Mrs. Varma's daughters are on the list. Priya and Ritu found their matches. But Sneha, who lives in Bangalore, didn't have a match from the Sharma family. So her corresponding result is null. Simple, right?
Okay, finally we get to the big one, the full outer join. I like to call this the Panditji's master list. This is the neutral matchmaker who steps in and says, enough with the preferences, just give me one single list with every single person from both families. Match them up if you can, and if you can't, just list them by themselves.
And to get this master list, we use the full outer join command. It doesn't care about left or right, it just grabs everything from both tables and puts it all together. Now look at this. This is the whole shebang. We've got our 2 happy couples, Rahul and Priya, Amit and Ritu. We've got our lone bachelor who didn't find a match, Samir. And we've got our bachelorette who's still looking, Sneha. Everybody is accounted for in one big comprehensive list.
All right, you've been doing great. So let's do a quick little pop quiz to make sure this is all sinking in. We'll call it the auspicious question.
Okay, put your thinking cap on for a second. If you wanted a list of only the boys who did not get a match, how would you do it? Which join would you start with, and what extra little condition would you need to add? I'll give you a second to think.
Did you get it? Here's how it's done. You'd start with a left join, right? Because that guarantees all the boys are on the list. Then, you just add a where clause at the end to filter for only the rows where the bride's name is null. And what's the result? It's Samir. Brilliant. See, you're getting it.
So this whole arranged marriage story has been a fun way to walk through the 4 types of joins. But what's the real point here? What's the story's real meaning for us? The real insight is this. Data sitting by itself is just a list.
The Sharma's list was just a list of names. The Varma's list was just another list. The magic, the story, the actual meaning only happened when we joined them, when we created a relationship between them. The power isn't in the tables, it's in the connections you can build between them.
So I'll leave you with this to think about. What stories are just sitting there, hidden inside your data, waiting for you to find the right join to unlock them? If this explainer helped things click for you, do me a favor and drop a comment below. Let us know which join is your favorite and why. And for more stories about code, make sure to subscribe. Until next time, keep connecting.
Welcome to The Explainer. Today, we're going to talk about deploying a secret agent right inside your database. Yeah, we're diving into a really powerful SQL technique that lets you ask way smarter, more targeted questions to get exactly the answers you're looking for. So, let's kick things off with a story. You've probably been in this situation, right? You're lost in this sea of options, looking for just one specific thing. Imagine this kid, Rohan, wandering through a massive, bustling marketplace. He's on a mission. Find the one shop that sells the absolute best extra crispy jalebi. Now, he could ask every single shopkeeper one by one, but wow, that would take all day. There's got to be a smarter way to do this.
And then, boom, Rohan has this light bulb moment. Instead of that brute force approach, he's going to be smart about it. He'll do it in 2 steps. First, he identifies the exact suite he's looking for, and then he asks the real question. Okay, who sells this specific thing? And you know what? That exact 2-step logic, that's how we can get way smarter with our own databases.
This clever little technique is called a subquery, and we're going to call it our spy inside the query. Seriously, just picture a tiny query with a singular mission. Go get one specific piece of information and bring it back to the main query. It's all about breaking down a huge, messy problem into these neat, bite-sized missions.
Okay, let's see how Rohan's mission actually looks in SQL. That inner query, that's our spy, right? It dives into the suites table with one job. Find the shop ID for jalebi. Now, let's say it finds a couple of them, maybe shop 101 and shop 204. It takes that list, that little piece of intel, and hands it off to the outer query. The outer query then says, great, now I'll just go to the shops table and find the names for only those IDs. See? 2 simple missions, 1 complex problem solved. Super elegant.
Now here's where it gets really interesting. Our spy isn't just a one-trick pony. Depending on the mission you send it on, the kind of intel it brings back can be totally different. The final report can look very different.
Basically, there are 2 main types of intel reports our spy can deliver. First, you have your single-row subquery. This brings back exactly 1 value, just 1 row, 1 column. Think of it like asking, what is the single most expensive suite? You expect 1 answer, right? So you can use simple operators like equals or greater than. But what if you ask for a list of all the shops in a certain area? Well, now your spy comes back with a list of values. That's a multiple-row subquery. And for that, you need a different operator, like in, to check if something is inside that list.
This is a brilliant example of a single-row subquery in action. Let's say you want to find all the cricket players from the same country as Virat Kohli. So, you send the spy in with a super specific mission. Go to the players table and find the country for the player named Virat Kohli. The spy runs off, does its thing, and comes back with 1 single word, India. Perfect. The main query now has its intel. It then just has to find every other player where the country equals India. Simple, clean, and incredibly effective. Okay, so up until now, our spy has been pretty independent, right? It goes on its mission, gets the info, comes back, and that's it. But what if the spy's mission changed depending on what the main query was looking at? This is where things get really cool. Our spy goes from being a simple messenger to a full-on undercover agent. This advanced technique is called a correlated subquery, and the key difference is huge. A normal subquery, it runs 1 time, period. A correlated subquery, our undercover agent, is totally different. It's constantly talking to the outer query. For every single row the main query processes, it runs again, sending back a brand new custom report just for that row.
Okay, let's look at a classic example. We want to find every single match where a player scored more than their own personal average. Now you'll see we're using these aliases, M1 and M2, to refer to the same matches table. And this is absolutely crucial. Here's how it works. The outer query, M1, picks up a row. Let's say it's a match where Virat Kohli scored 122 runs. It then turns to the inner query, our correlated subquery, and says, hey, for this player, What's his average score in the M2 table? The inner query calculates Coley's average and sends it back. Then the outer query checks, is 122 greater than that average? Yep, cool, that's a result. Then it moves to the very next row and does the whole dance all over again for the next player. It's a really powerful row-by-row investigation.
This kind of power naturally brings us to one of the biggest debates in SQL, the showdown. When do you use a subquery, and when do you reach for its famous, often more powerful cousin, the join?
I think the analogy holds up perfectly. A subquery is like sending a messenger to get a single piece of info. Hey, go get me the price of bread. A join is totally different. That's like inviting the baker and his entire staff to your table to combine all your information into one giant spreadsheet. A subquery is for filtering, a join is for combining.
So what's the bottom line? Well, you're looking at a classic trade-off. Subqueries are often way easier to read. The logic is all nicely wrapped up. It just makes sense. But 9 times out of 10, joins are going to be faster because databases are built to optimize them. So the real question you have to ask yourself is, what do I need in my final result? If you only need columns from your main table and you're just using the other table to filter, a subquery can be really clean. But the moment you need columns from both tables in your final output, yeah, you're going to need a join.
All right, that was a whirlwind tour of SQL Spycraft. Let's do a quick mission debrief and lock down the key takeaways.
So, think about the tools you have now. You've got your single-row subqueries, perfect for when you need just one specific fact. You've got your multiple-row subqueries for when you need to check something against a whole list. Then there's the heavy hitter, the correlated subquery, your undercover agent for those really complex row-by-row jobs. And maybe most importantly, you now have a framework for deciding between a subquery and a join based on that trade-off between readability, performance, and what you actually need in your results.
But I've got one last secret for you, a final plot twist in our spy story. We've been saying joins are usually faster, and they are, but not always. Modern database optimizers are incredibly smart, and sometimes a well-written subquery, especially with in, can actually outperform a complicated join. So what's the real takeaway? What's the ultimate rule of data spycraft? It's simple. Test everything, never assume. The only way to know for sure is to measure. So there you have it. You're now armed with some serious SQL spycraft, ready to write smarter, more elegant queries. And that leaves us with just one final thought for you. What's the most complex, the most tangled, the most "I can't believe I got this to work" query you've ever written? We all have those war stories. Think about it. Until next time. Keep on explaining.
Hey everyone, and welcome to The Explainer. Today, we're cracking open a secret recipe book, one that's going to turn your messy, complex SQL queries into something clean, elegant, and believe it or not, easy to read. So let's get cooking.
You know what this sounds like? It sounds like what happens when you just throw a bunch of ingredients into one big pot and just, hope for the best. It's also exactly what happens when you try to write a really complex SQL query all at once. It just becomes this confusing jumble that's a total nightmare to debug. But what if I told you there's a much better way?
I want you to think about writing SQL like you're cooking a masterpiece. Let's say a truly fantastic Hyderabadi biryani. A great chef doesn't just chuck everything in a pot. No way. They prep everything separately, right? You've got your marinated meat in one bowl, your crispy fried onions in another, the perfectly cooked rice in a third, and only then do they bring it all together. Well, we can do the exact same thing with our code, and the tool that lets us do it is the Common Table Expression, or CTE.
So what exactly is a CTE? It's basically one of those prep bowls from our kitchen analogy. It's a temporary table that you give a name to. But here's the key. It only exists for the single query you're about to run. You prepare a little piece of your data, you give it a name, and then you use that neat little package in your final query. Simple as that.
And the syntax? It's beautiful. It's so simple. You just start with the keyword with. This basically tells your database, hey, hang on a second. Before we get to the main event, let's prep this little ingredient bowl. You give your bowl a name, you define what goes inside it with the normal select statement, and that's it. Then you can use that name in your final query just like it was a regular table.
All right, enough with the analogies. Let's see how this recipe actually works with a real-world example. Imagine we're working for an e-commerce company, and our boss asks us to find the total amount spent by every customer who lives in Mumbai. This is a classic two-step problem, perfect for a CTE.
Okay, so first up, we've got our customers table. Pretty standard stuff. We're only interested in Rohan and Arjun here, since they're our customers from Mumbai. Our first job is to isolate just these two.
And second, here's our orders table. This has all the spending data.
and you can see it's linked by that customer ID. We're going to need to sum up these amounts for each person. So here we go. We start our recipe with our first CTE. We use that with keyword to create a temporary table, and we'll call it Mumbai customers. This is our first prep bowl, and it only has one thing in it, the customers we care about. It's simple, it's clean, and it's totally isolated from everything else.
Next, we just add a comma, and we can define our second CTE right away. We'll call this one total spend. And look, this bowl has one job and one job only. Calculate the total amount spent for every customer and put it in a nice clean column called total amount spent. And now for the final assembly. Just look at how clean and readable this is. Our main query isn't some horrible nested mess anymore. It just says, hey, take our Mumbai customers bowl and join it with our total spend bowl. It practically reads like a story, which makes it so much easier to understand and to fix if something goes wrong.
But wait, there's more. CTEs aren't just about keeping your code tidy. They have a secret superpower, a real pro-level technique called recursion. This is where a CTE can actually refer to itself to solve incredibly complex problems, like navigating through any kind of hierarchy.
Okay, check out this employee table. It's a classic company org chart. Now let's say our goal is to find the entire reporting chain for Ishan, the developer, all the way up to the CEO. Seriously? How would you even do that with a standard join? It would be an absolute nightmare of self-joins.
A recursive CTE solves this so elegantly, and it really just has two parts. First, you've got the anchor member. This is just your starting point. In our case, it's Ishan. This part only runs one time. Second, you have the recursive member. This is the part that loops. It joins the table to the results of the last step to find the next person up the chain.
So let's trace how this actually works. On the very first run, the anchor part fires off. It goes into the table, finds Ishan, and we'll say he's at hierarchy level 0. Right now, our temporary CTE contains just one person, Ishan.
Okay, now the magic happens. The recursive part kicks in. It looks at the result from the last step, which was Ishan, and finds his manager's ID, which is 4. It then looks up employee ID 4 in the main table, finds Dia, and adds her to our results at level 1.
And we do it again. The loop runs, and now it looks for Dia's manager, which is ID 2. The query finds Bhavna in the employees table and adds her to our growing list of results, this time at level 2. See the pattern?
One more time. The query looks for Bhavna's manager, ID 1, and finds Arav, the CEO. He gets added to our results as level 3. And just like that, we've built the entire chain of command from the bottom to the top. So why does it stop? It's actually super elegant. On the next loop, it tries to find Arav's manager, but his manager ID is null. The join condition fails, no new rows get added, and the recursion just stops. All done. You've just walked an entire hierarchy with a single, readable query. That's power.
Okay, so you've now got this fantastic new tool in your SQL toolkit. It's a real superpower. But the big question is, when should you actually use a CTE instead of, say, a good old-fashioned subquery or a temporary table?
Well, this table gives us a pretty clear rule of thumb. A subquery, it's okay for something really simple, but it gets messy and hard to read fast. A temp table, that's a different tool for a different job. It's great when you need to reuse the same data across multiple, separate queries. But for making a single, complex query easy to read, or for that unique power of recursion, the CTE is absolutely the way to go.
So let's just sum it all up. You're going to love CTEs because they make your code readable and maintainable, just like a good recipe. They let you easily debug or change one little step without breaking the whole thing. You can reuse a CTE multiple times in the same query. And, most importantly, they unlock that incredible magic of recursion. This isn't just about writing cleaner code, it's about solving a whole new class of problems.
So the next time you find yourself facing down a monster of a query, don't just throw all the ingredients in one pot. Channel your inner master chef. Use that with clause and build something that's not just powerful, but beautiful. And that leaves me with a question for you. What's the most interesting hierarchy you can think of? A family tree? The dependencies for a big project? Maybe even the whole evolutionary tree of life? With a recursive CTE, you now have the power to explore it.
Hey everyone, and welcome. Today, we're diving into a part of SQL that honestly feels like a bit of magic. We're talking about window functions. And to really get our heads around them, we're going to use an analogy I think we can all relate to, the classic annual school photo. Oh, you remember this day, right? The one day of the year where everyone's uniform was actually clean, your hair was combed, for once. It was class photograph day. And remember how the photographer would get everyone organized? Okay, short kids in the front, tall ones in the back. And then a teacher would always jump in. Wait, let's get the houses together. Oh, the red house kid's over here, blue house right in the middle. So when you look at that final photo, you can zoom in on one student. Let's call her Priya. You see her as an individual. But you also see her in context, right? You see who's standing next to her, you see she's in the second row, and you see she's part of the blue house. Her own info is still there, but she's also clearly part of a group, or what we're about to start calling a window. And this brings us to a really interesting problem. What if you wanted to see Priya's exact height, but at the same time, you wanted to see the average height of just her blue house? How could you possibly see both of those things at once? In the world of data, this kind of question comes up all the time. Now, your first instinct in SQL might be to use group by, but look what happens. Group by is like telling the photographer, just give me the average height for each house. You get your 3 averages, but poof, Priya's gone. All the individual students have vanished. The rows are collapsed. But a window function, that's like a magic lens. It keeps every single student in the picture and just adds that group average right next to them. And that is the magic of SQL window functions. They're that special lens for our database photographer. They let you run calculations on a set of rows, that window, without squashing all the individual rows. You get the fine detail and the big picture all at once. So to get a little more technical, what is a window function? Well, it's just a calculation that happens across a specific set of rows that are related to the current row. The key, the absolute most important part, is that it doesn't collapse your original data. And the secret sauce that makes it all happen is one little command, the over clause. So let's talk about this magic over clause. The best way to think about it is that it's the list of instructions you're giving to the photographer. It's how you tell SQL exactly how to frame the shot, how to define that window of rows that you want to do your calculation on. Okay, let's get our hands dirty with a real example. We've got this simple student marks table. We have names, subjects, and the marks they got. And our goal is to see how each student's mark compares to the average for that subject. So the very first instruction we give inside that over clause is partition by. This is, and I mean this literally, the same as telling the photographer, okay, group everyone by their house. In SQL, partition by tells the database to chop up the data into these little separate groups or windows based on whatever column you tell it to. For instance, if we say partition by subject, you can see what happens. SQL logically creates 2 separate worlds. You've got your maths window over here and your science window over there. Any calculation we do now will happen inside these windows, completely independent of each other. And now check this out. Here's the result. We wanted the average mark for each subject, so we wrote AVG marks over partition by subject. Look what it did. For the maths partition, it calculated the average, which is 91, and stamped that value next to every single row in the maths group. Then it did the same for science. And the best part? Priya's individual score of 95 in maths is still there. No data lost. That's the power. Okay, on to our next trick. Aggregates like average are cool, but what about ranking? This is like asking the photographer, okay, you've got them in their houses, now line them up from best to worst score. To do this, we just add another instruction inside our over clause, order by. For this, let's switch to a more, businessy example. We've got an employees table with departments and salaries. Now, I want you to pay close attention to this. In the finance department, Ramesh and Suresh have the exact same salary. That tie is going to be super important for understanding how these next few functions work. First up, the rank function. We've partitioned by department and ordered by salary, from highest to lowest. So as we'd expect, Ramesh and Suresh are tied for the highest salary in finance, so they both get rank 1. But look at Ram, the next person. His rank is 3. Rank works like a competition. If 2 people tie for first place, the next rank gets skipped. There's no rank 2. Now, contrast that with dense rank. Same setup, same tie for first place. Ramesh and Suresh are both rank 1.
But look at Ram now. He's rank 2. Dense rank is dense. It doesn't leave any gaps in the numbers. This is really useful when you just want a straight sequential ranking.
And finally, there's row number. This one is simple. Its only job is to give every single row a unique number, in order. It doesn't care about ties in the data. Even though Ramesh and Suresh have the same salary, row number gives them different numbers, 1 and 2. It's perfect when you just need to slap a unique ID on each row in a sorted group. All right? You ready for this? This next set of functions is where things get really cool. So we've grouped our students. We've ranked them. What if you wanted to peek at the value from the row right before you, or the row right after you? To look at your neighbors in the line, you meet lag and lead.
Here's lag in action. Let's say we have monthly sales data. To see how this month did compared to last month, we can use lag monthly sales. And for each row, it literally just reaches back to the previous row and pulls that value forward. So for February, we see January sales right there next to it. Think about it. Calculating month-over-month growth just became ridiculously simple. And as you might guess, lead does the exact opposite. It looks forward.
Okay, pop quiz. Let's see if this is all clicking. Imagine you're analyzing cricket data for the IPL. You've got a table with players, their teams, and their total runs. You want to find the top 3 run scores within each team. So inside that over clause, what column are you going to partition by, and what are you going to order by? Take a second. Did you get it? The answer is you'd partition by team because you want to create those separate little groups for each team, right? And you'd order by run score DESC to line up the players from highest score to lowest within each of those team windows. With that one query, you can rank everyone and then just pick off the top 3. Awesome. All right, we have all the building blocks. So let's move beyond the school photo and see how these tools solve actual business problems. We're going from photos to profits. Here is a super common business request. Find me the top 3 salaried employees in every department. Now, you can't filter on a window function directly, so we use this really clean 2-step pattern. First, we use something called a common table expression, or CTE. Just think of it as a temporary little table. In that CTE, we rank everyone in their department. Then, in the second step, we just select from that temporary table and filter where our new rank is 3 or less. It's a powerful and super readable way to solve this. Here's another business classic, calculating a running total. You have no idea how painful this used to be to write in SQL. Now, it's almost laughably easy. You just use sum sales with an over clause that orders the data by date. For every single row, SQL sums up all the sales from the very beginning up to that point. It's elegant, it's efficient, and it's incredibly useful for tracking cumulative growth. So, as we start to wrap this up, I really want you to appreciate the bigger picture here. Learning window functions isn't just about memorizing some new syntax. It's about fundamentally changing how you see and interact with your data. So let's just nail down the key takeaways one more time. First, window functions let you do calculations on groups of data without destroying the original rows, which is the big difference from group by. All the magic happens in the over clause. We use partition by to make our groups and order by to sort inside those groups. And we can use them for everything from simple sums to complex ranking to amazing period over period analysis with lag and lead. And this, really, is the most important idea of all. Window functions actually change how you think. You stop looking at your data as just a flat list of rows. You start to see every single row in its proper context, in relation to its group, its category, its previous time period. And when you can see those relationships, you can answer incredibly complex questions with surprisingly simple, clean code. So, I'll leave you with a final question to get your own brain spinning. Now that you have this new magic lens, what's the most interesting, most creative analysis you can think of? Doing with lag or lead? Think about user behavior, financial trends, inventory changes. The possibilities are pretty much endless. Thanks so much for joining this explainer, and happy querying.
Welcome to the explainer. You know that classic road trip argument, right? The one about who gets to control the music? Well, today, we're going to take that exact argument and turn it into a super powerful data skill. This whole playlist battle is going to teach you everything you need to know about SQL set operations. And trust me, these are some of the coolest, most elegant tools you can have in your SQL toolbox.
So, here's what we've got on deck. We'll kick things off with the playlist battle. Then we'll cover 2 golden rules you absolutely need to know. After that, we're diving straight into the operators, union, intersect, and except. And to wrap it all up, we'll talk about why you might use these instead of joins. Let's get into it.
All right, so picture this. 2 friends, a long road trip ahead of them, and a problem that is, at its heart, a data problem, even if they don't realize it. Their little debate over music is the perfect setup for what we're about to solve using SQL. So let's meet our friends. We've got Rohan, who's all about classic rock anthems, and Priya, who loves her Bollywood dance hits. You see, their friendly argument is exactly what we do with data all the time. We have different lists of information, and we need to figure out how they relate to each other, what's the same and what's different.
Okay, so to make this real for us, let's just imagine their playlists as 2 super simple tables in a database. On the left, you see Rohan's playlist. On the right, Priya's playlist. Now take a look. You probably spotted it already. They have one song in common, Chaya Chaya. That little bit of overlap? It's going to be really important in a minute. These 2 tables are our playground for today.
So how do they solve this? Well, the answer isn't in the car stereo settings. Nope, it's in SQL. The solution is something called set operations, a handful of commands that are literally designed to combine, compare, and contrast lists of data, just like their playlists.
But before we jump in and start writing any code, hold on. We need to talk about the foundation. There are 2, let's call them golden rules for set operations. They're non-negotiable. If you get these wrong, your query just won't run. So let's lock these in first.
Here they are. Rule number 1, your select statements have to pull the same number of columns. Simple enough. Rule number 2, the data types of those columns have to be compatible. I mean, it just makes sense, right? You can compare a list of text with another list of text, or numbers with numbers, but you can't really combine a list of song titles with, say, a list of album release dates. SQL knows this, and it'll throw an error.
All right, with the rules down, let's get our hands dirty with our very first operator. This one answers Rohan's big question. How do we just create one massive, epic road trip playlist with everything from both lists? Well, the tool for that job is union.
So, what does union actually do? It takes the results from 2 or more select statements and stitches them together into one list. But here's the magic bit. The key thing you gotta remember about a regular union: it automatically finds and gets rid of any duplicates. It just cleans up the list for you.
And the best part? The code for this is ridiculously simple and easy to read. You just write your first select statement, type the word union, and then write your second select statement. That's it. You're basically just telling the database, hey, give me the unique combo of these 2 lists. And boom, here's what you get back. One single unified playlist. Now look closely. Remember Chaya Chaya? It was on both of their lists, but in our final result, it only shows up once. That's union doing its job perfectly, making sure we have a clean master list with no repeats.
Now, this is a really interesting choice you get to make. What if you actually wanted the duplicates? Maybe you're not making a playlist, but you're trying to count every single entry. Well, for that, you've got union all. It just smushes the 2 lists together, warts and all. So the trade-off is pretty straightforward. Union gives you that clean, unique list, but it's a little bit slower because it has to do that duplicate check. Union all is way faster because it skips the check, but you'll get every single row from both tables.
Okay, on to the next challenge. Remember Priya's request? She wanted to find the songs that they both liked, the ones that were on both of their playlists. So, how do we find just that common ground between their 2 lists? For that, we use intersect. Yeah, think of this as your common favorites button. It compares 2 lists and gives you back only the rows that are in both of them. The query is just as easy as union. You just swap out the keyword. Let's see what that gets us.
And there it is, just like that. The intersect query perfectly isolates their common ground, Chaya Chaya. It's such a precise tool for finding that valuable overlap between any 2 sets of data.
And this isn't just for music playlists, of course. This logic is super powerful for all sorts of real-world problems. Imagine you're working with a huge movie database. You need to find all the sci-fi films that also have deleted scenes. Easy. You get a list of all sci-fi movies, a second list of all movies with deleted scenes, and Intersect will instantly show you only the movies that are on both lists. Perfect.
All right, time for the final piece of the puzzle from our road trip duo. Rohan got a little curious. He wanted to know which songs on his list were totally unique to him, the ones Priya didn't have. This is all about finding the differences, and for that, we have the except operator.
Now, this is super important. Except is all about direction. It gives you the rows from the first list that are not in the second list. That means the order you write your tables in matters a lot. It completely changes the question you're asking. Oh, and a quick heads up. If you're using an Oracle database, this operator is called minus, but it does the exact same thing.
So let's see this in action. First, we'll ask the database, give me the songs from Rohan's playlist that are not in Priya's playlist. And the result? We get his 2 classic rock anthems. These are the songs that are 100% unique to his list.
Okay, now watch what happens when we just flip the query around. Now we're asking for the songs in Priya's list that are not in Rohan's. And see? A completely different result. We get her unique Bollywood hits. This shows you perfectly that with except, your perspective, which table comes first, defines the entire outcome.
Now, I know what some of you are probably thinking right now. Wait a minute. I'm pretty sure I could have done all of this with some clever joins and where clauses. And you know what? You're absolutely right. You often can. But there are really good reasons why set operations are often the better choice. It all comes down to things like readability, logic, and sometimes even performance.
And this slide lays out the difference perfectly. On the left, using except is declarative. It describes what you want. Give me stuff from A that's not in B. It's clean and logical. The complex join on the right is procedural. It describes how to get the answer step by step. The except query is way easier for a human to read, and often it's more performant because you're telling the database your ultimate goal and letting it figure out the best way to get there.
So let's do a quick recap. You've basically just added 4 awesome and really logical tools to your SQL toolkit. You've got Union for combining lists and ditching duplicates, Union All to combine everything and keep the duplicates, Intersect to find that crucial common ground, and Except to cleanly find what's unique from one list's perspective.
And so I'll leave you with this question. Think about the data you work with every single day, whether it's for your job or just a personal project. Where do you have separate lists of things? Customers, products, users, events? Where could a simple operator like Intersect help you instantly find that valuable common ground and maybe unlock a brand new insight? You're the data DJ now. Happy querying.